Hi everyone, thanks for joining us for another hangout with the OpenPOWER Developer Challenge technical team. Today we're going to be covering using the SDAccel integrated development environment to easily do FPGA programming in SuperVessel for your OpenPOWER Developer Challenge. On the agenda, we're going to have an introduction to SDAccel, what it is, what you can do with it. And then we'll do a live demo of actually using it in SuperVessel. And then we'll talk a little bit about some things that are currently in development that will allow you to blend using the SDAccel environment with Cappy, the coherently attached processor interface. And then we'll have plenty of time for Q&A at the end. So on the call today, I'm Beth Ann Noble from IBM, and we also have Mike Hollinger, our technical expert for the Developer Challenge. We have Fernando Valina from Xilinx, who's going to introduce us to the SDAccel environment. And then Ishan Dalal, also from IBM, who's going to take us through a demo and talk about Cappy and SDAccel. So we're all here on the call, and you can ask questions anytime. We'll take time to answer those at the end. And we're also all in Slack, so you can see our handles here on our profiles, and we'd be happy to follow up with you anytime in the Slack environment with your questions. So I'll hand it over to you, Fernando. Thank you.
Thanks, Beth Ann. So let me start sharing my screen, and we can get started. So today I'm going to continue the introduction of SDAccel and talk a little bit about our compiler environment and walk through an application optimization. So how are you going to change your code so that you get the best performance out of the solution on SuperVessel? So SDAccel, as a refresher, is a compiler environment that will take your OpenCL application code and your kernel code, and it will compile it down to FPGA accelerated boards that are connected to PowerRate servers. So out of SDAccel, you'll get two things. One will be a binary container, which will be the programming part for the FPGA. This will be the OpenCL kernel code. You can also write it in C and C++, or you can use a library from one of our partners. In addition to this, you will get the OpenCL runtime library that's provided by Xilinx. And what the runtime library does is it provides the link between your host code application running on the Power processor to the FPGA. It takes care of configuring the FPGA with the right accelerators, starting your accelerators, transferring memory, and setting up and monitoring the correct execution of everything. So one thing to keep in mind is that creating designs in SDAccel, you're not targeting a fixed architecture. Your architecture is created based on the kernels that you have in your program. This means that compile times will take a little bit longer than you would expect for a CPU or GPU because you are creating the hardware as you go. So because of the difference in compile times, we have added two additional steps into the flow, which allow you to verify the functional correctness of your design and also ensure that the design will fit onto the FPGA device. So the first step is what we call here step 3, which is the first step in the tool, which is simulating your design, compiled everything against the host processor. So this is a software-only execution of your entire application. Your kernels are not parallelized. This is a functional check only. This will ensure that you have the right API calls happening between the host and the kernels, and that you're transferring the right data over and receiving the correct results. After you're happy with the functional correctness of the application, we have what is called hardware emulation. So the whole point of hardware emulation is now you want to look at the capabilities of the design. So what is the performance you're going to get on the FPGA? Hardware emulation is a hardware simulation of your accelerators, which means that you will simulate every gate, every net in your logic design. And this will give you a cycle-accurate timing report of how fast your accelerators will run once they're compiled to the FPGA board. So the key point of this step is to analyze major bottlenecks in how you're moving data from your accelerators to memory and back. One thing to keep in mind is that FPGAs do not have a cache structure inherent to the fabric, such as a GPU or a processor. Any kind of data caching or data reuse has to be recoded as part of your algorithm or as part of your kernel code. The compiler will take care of implementing the architecture that is expressed by your code, but it does not create additional structures that are not present in your code, even if they improve performance. So once you're happy with the overall performance, the next step is to compile it for the FPGA device. This step, it takes about an hour. So the generation of brand new hardware specific to your application will take about an hour to compile. And then you can run it on one of the boards that is hosted on SuperVessel. So these are the main 3 steps of the SDAccel flow. Next, I'll go into a few more details about things you need to watch out for when you're optimizing your designs. So first thing to keep in mind is the system bandwidth characteristics. So for both Vertex cards and UltraScale cards that are hosted on SuperVessel, we have specific characteristics in terms of how much data throughput we get moving data between the host and the FPGA. So if you look at transferring on the Vertex 7 cards, which are available as part of the OpenPOWER challenge, your maximum throughput is going to be about 4.5 gigabytes per second bandwidth. And if you're reading back from the FPGA, you're going to get about 3.5, 4 gigabytes per second. Now, this all works at this bandwidth if you follow 2 things. One, you do not interleave reads and writes from the FPGA card, because if you do concurrent reads and writes, today you only get 2.5 gigabytes per second. And the other thing is that your transfers have to be of a large size. So small single byte-size transfers will give you almost no performance, and to get reasonable performance, you need at least a couple megabytes of data that you're pushing through on every buffer. And the same thing applies for the UltraScale card. So this is the PCI interface. It's a PCI Gen 3 by 8. So once you accounted for this, the other thing to take into account is the bandwidth of your accelerators to the memory that's on the FPGA card. So both cards have 8 gigabytes of memory available on the Vertex 7 card and 16 gigabytes of memory available on the Kintex UltraScale card. For both of these cards, the maximum achievable bandwidth from the FPGA fabric out to DDR, and these are all DDR3 based designs, is the same. So at best performance, you will get 8 gigabytes per second on your design, your algorithm, so that it's doing burst transfers, and it is using all the data width that's available in the FPGA. So to achieve maximum bandwidth of 8 gigabytes per second, your kernels should be fetching 512 bits of data every time, or if you're using OpenCL types, a float 16 or an int16 data type should be on your interfaces. Anything below that, your performance will start dropping, as is shown on the curve on display. So how do we take this all? And the final thing to keep in mind is the impact of starting your kernels from the host to the accelerator. So today, the scheduling and launching of accelerators is all contained inside the runtime process that's running on the host processor. We are polling the FPGA card to figure out the status of all accelerators and of the kernels. And there is a startup time from starting the kernel, as well as with sending parameters over to the FPGA. So parameters that are going to the accelerators are not sent through a DMA transfer, they're sent through the PCIe bar interface, which is slower. So the more parameters you send as part of your function interface, the longer it will take to launch the kernel, as shown by the curves on the chart. So as a general rule of thumb, a handful of parameters doesn't make any difference in the time it will take to start your accelerator. If you have hundreds of parameters you want to send through, it's best to group them into an array or a buffer that you can send as a burst through a DMA transfer to the FPGA DDR memory, and then allow the kernel to read those configuration parameters out of the buffer in memory. That will give you the best performance. So let's look at an optimization example and how we put all of this together. So for this example, I'm taking a very simple filter that is doing a denoising function, so a medium filter. You have an original image that has some noise on it, and the output is to be smoothed out or cleaner. So just a quick overview of the algorithm. This is a windowing algorithm based on a 3x3 window. So you have a set of 9 pixels that are used to compute a center pixel. Now, the 3x3 window is reused, and your data is reused through the lines as it's progressing through. Now, if we look at the host code For this example, it's going to look very similar to every other example that's targeting FPGA in that your host code will create a buffer, it will allocate some memory on the FPGA card, it will send the data over to the FPGA card using the CLNQ write buffer function, and then it will launch the FPGA accelerator and wait for the events to read it back. So that part's cookie cutter. It's going to be the same for almost all applications. The only difference is going to be how many buffers you're sending to the FPGA device, how many times you're enqueuing tasks on the FPGA. But the structure and the API calls are going to be the same. The more interesting part is what happens on your FPGA kernel code. So in terms of your kernel code, here is a first implementation of the medium filter. This is a functionally correct implementation that assumes that the kernel knows about the entire image size that you want to compute, and the image size is configurable through the host using the width and height parameters. And it's assuming that the global size and the group size that is local size that is seen by both the kernel and the host is 1, 1, 1. So very simple example, this is functionally correct code. Now, when we run this, you'll see that our hardware emulation stages and also running on the board will produce a profiling report. The profiling report here says that for my example test bench where I'm calling the medium filter with one image, my kernel gets executed once, which is what I expect, but the total computation time is 464 milliseconds. This is extremely slow, especially if I want to try to achieve a live video frame rate, so at least 6 milliseconds maximum per frame. So the kernel is slow, but there's other places to look at first. Before focusing on the data path, we want to focus on how is this kernel accessing memory, because a lot of your latency is going to come from waiting for data to come out of DDR into the FPGA fabric. So if we look at the data transfer summary that's part of this report, you'll see that there's a row for the kernel reads and the kernel writes. The kernel writes don't seem excessive. There's only 128 of them, so that's probably okay. We're not really going to focus on that. What we're going to focus on is on the kernel reads, these 147,000 reads of data. Now, as we saw in the algorithm description, there is a lot of data reuse that is possible in this algorithm because you're computing over 3 lines of data and it's a sliding window. So why is this code behaving so inefficiently? So the reason is that the original code, and here I have an expanded code view of the original code, is creating my 3x3 window that is computing, and it's fetching every pixel out of this memory called input. Input is my global buffer for the input image that was passed from the host to the FPGA card. This means that for every pixel computation, we're doing 9 pixel reads out of DDR memory. Now, if you keep into account that the maximum bandwidth we have available on the FPGA card is 8 gigabytes per second, this starts to add up very quickly into an inefficient memory use. And also keep in mind that that 8 gigabytes per second was assuming a burst of at least 64 elements and 512 bits. So bringing in 1 pixel at a time is not going to give you any performance. And you can see from the trace view at the top that at the bottom you see the kernel is running, so you see the solid green bar, and you see at the top the reads and the writes, and there's a lot of white space or gaps. Those white spaces and gaps signify times when the accelerator is actually stalling, waiting for data. So it's sitting idle, it's not doing anything. Your results aren't getting computed because you're waiting for new input data. And this is something that adds up very quickly in terms of your performance. So the first thing we want to fix is how is this data used. So as I mentioned before, the FPGA doesn't have cache units inherent into the fabric. So you have to build it as part of your application code. The way to build it as part of your application code is to declare it in terms of using local buffers in your kernel definition. So if you look at the top, the first change we did to this code is we allocated 4 line buffers, 3 for the input, 1 for the output line, to the maximum width that we expect this kernel to work at. So for any kind of processing workloads where you have a variable size of how much data you may produce, your buffers that are going to be implemented in hardware need to be sized to the worst case of your data width. So, you know, if in most of the cases, for example, in this image, I'm doing a 1000 by 1000 pixel image, but I have the off chance of doing a 4000 pixel image my buffers need to account for 4,000 pixels so that your hardware can accommodate different usage scenarios that you're expecting. Once you've declared these local buffers, the next step is to infer the bursting so that you can get the full reads bandwidth out of DDR. This is done with the async workgroup copy API from OpenCL, which has the same functionality as the C and C++ memcopy API. So here we're copying in the 3 line buffers, and then we go into processing of the pixels. So first thing we want to do is we want to change the code we originally had, so my 3x3 local window RGB, which was reading out of global memory, and have it read out of the local line buffers that we've just created. This will allow you to do some data prefetch, so you're prefetching full lines of data before you're actually needing the pixel, and reuse them as the window slides through the image. So what this will achieve is your hardware element will have 3 modules. One will be the read unit, one will be the compute, and the write back. So the read unit will fill in 1 buffer at a time, and your compute unit will, once this operation is done, will read all 3 line buffers in parallel and slide the window through, creating results for the output line buffer. Once this buffer is full, the write back unit will send it back to DDR as you're starting to process the next image. And you can overlap the reads of image 1 with the write of image 0. So what does this get us in terms of changes? So by doing this recoding, we can see in the trace view that our overall green bar of when the kernel was running is has been reduced, and there is almost no gaps between my reads and writes operations in terms of my memory transfers. So I see now that my kernel went from 400 milliseconds to 163 milliseconds. Still not what we want, but it's going in the right direction. And if I look at my memory reads and writes, they're about the same, they're balanced. So most likely the next problem in the design doesn't have to do with your memory access. So the next thing we want to look at is how do we get this to work in parallel? So one thing that the compiler will do is it will create an implementation of your kernel that is functionally correct but uses the minimal amount of resources in the FPGA fabric. So unlike a fixed architecture such as a CPU or GPU, where you can throw as many lines of code as you want at it, and the real issue you'll have is performance, because your code will run, it'll just take more time to run. In the FPGA, lines of code translate into physical resources that are used to implement that functionality. That is custom to what those lines of code express. So not all of your code will fit, and in that regard, any change that improves performance but will consume more resources is required to be a designer objective. So you as a designer need to tell the compiler that you're willing to spend more resources to improve performance. So the way to do that in the compiler is through attributes in your code, in this case the OpenCL XCL pipeline loop attribute, which is unique to Xilinx. And this will tell us that we want to run an iteration of this for loop, this for X loop, as fast as possible. So every clock cycle, I want to start processing the next pixel. I don't want to wait for my entire pixel results to be computed before I start fetching data for the next one and start computing it. So what is this results engine? Without the pipeline attribute, you can look at it as for every pixel you're reading, you're computing, and you're storing, and then you read, you compute, and you store, and so forth, pixel by pixel. And that's where we get the 160 milliseconds. But if you think of this spatially, your read unit could be reused for the next pixel as soon as it's finished fetching all the data for read 0, for pixel 0. Same as the compute unit. It could be reused immediately. So if I look at this time scale and you consider the first box should be time 0, time 1, and time 2, once I get to time 2, I am storing back the results of pixel 0, I'm computing the value for pixel 1, and I'm already fetching the new data for pixel 2. This allows me to have multiple pixels in flight in my data path, keeping all my hardware units that have been created for this algorithm busy. And this is what's going to get you the performance. So in terms of the results, the benefit of this, we went from 160 milliseconds to 6 milliseconds of execution. This satisfies our design goal, and with simple changes, you can get the performance in your design. So a couple of things to keep in mind is when optimizing any design targeting FPGA boards, the first thing to look at is how are you handling memory transfers between your kernel and global memory. Are they bursting transfers? Are you using all the bit width that's available in the FPGA device? And how many of those transfers are you initiating? Once you fix those memory transfers to the point where they're at their minimum number of unique transfers, the next thing is to look at the data path. And in the data path, you want to identify loops such as this one, which could be pipeline. So one of the effects of pipeline that I didn't mention is that any loop within this context will be unrolled. So in this case, I had a sequential loop here doing one color channel at a time. So it was giving me minimal hardware resources. It was using only one multiplier and reusing it across the 3 channels. By pipelining the X dimension loop of the image, the channel loop gets unrolled, and I get the 3 multipliers for the median function, so my 3 color channels are done in parallel. And this also gives you better performance. It costs a little bit more resources on the FPGA device, but your performance trade-off is worth it in most cases. But once again, that's a designer choice, and it depends on your specific algorithm, which part of your algorithm you want to accelerate more or use more resources on to meet your design goals. So this technique that I went over applies to every single design you will be doing on SDAccel, and it is covered in our user guides and our optimization guide. So one good resource for you is to look at the SDAccel optimization guide that's available on xilinx.com/SDAccel. This will go into detail over the memory optimizations I just mentioned and also the pipelining optimization. We do have getting started examples available on GitHub that you can use to look at how to optimize your code. Specifically, if you're doing complex data transfers, to have data constantly going from the host to the FPGA while the FPGA is processing something. The SHA-1 is an excellent example of how to manage this. If you're doing more of an image processing application and you want to maximize the throughput, both the histogram equalizer and the medium filter are excellent examples on how to handle and build custom memory architectures inside of the FPGA. We have getting started videos that give you an overview of the application, and then of course you can run all of this on SuperVessel using the FPGA boards that are provided on it. So with this, I will hand it over to Ishan for a demo of the SDAccel service on SuperVessel.
Great, and thanks. Just before we move on, I wanted to point out that if any of our OpenPOWER challengers would like to sign up to use SDAccel and SuperVessel, you go directly to Xilinx, and there's a bit.ly here, bit.ly/SDAccelSV. And when you fill out the application workload box, it would be really helpful to mention that you're working in the OpenPOWER Developer Challenge, so that'll be flagged for priority. So, and I shared that in the showcase for anyone viewing right now. All right. I'll hand it over to you, Ishan.
Thanks, Bethan. Thanks, Fernando, for the detailed explanation. I'll show the demo of Hello World example that we have running on the SuperVessel. Let me start the screen share. Okay, so this is the SDAccel homepage on SuperVessel. In the overview section, you have got all the details about how to manage your code online on SuperVessel and how to compile and optimize it. There are a couple of documents that are there in the overview. One is the optimization guide that is similar to what Fernando went through in the median filter example. Then there is the OpenCL standard for parallel programming. In the document section, we have the white paper, the user guide tutorial. The most important thing that I will point to people who are going to start with SDAccel would be the examples which are there on GitHub. It covers a variety of examples. The initial examples, they show they have the hello world and dot product, then vector multiplication addition, which should be pretty straightforward and will give you guys a good hands-on experience of the tool and the development environment. Then the real-world examples there are in various fields like acceleration, which correspond to the encryption, decryption, then image processing, data mining. As you can see here, there is the histogram equalizer, then Bitcoin mining, edge detection, and everything. So once you get a good hang of the tool, then you can try these examples out and see the performance difference using the optimization techniques that Fernando discussed. So let me begin. Today we would go through the hello world example. It's a simple example in which the host will send a bunch of values to the kernel that is working on the FPGA, and the FPGA will print those values out and give it back to the host. So give me one moment. Right. So you click on the new project tab and you give the name. Just give a brief description of what you're going to do and submit it. Then click on the project name. It will give you options about the files that you want to add, which would be your source code that includes the host code and the binary OpenCL or RTL code. So click on the code file. Here, the input should be a zip file, and it will be automatically unzipped when you open it. So I have it zipped in hello.zip. As you can see, there are a number of files over here. We have the host file, then the OpenCL file, that is the kernel hello. Then the data files would be for applications in which you need to give an input along with your source code. For example, if you have an image processing application like a Sobel filter or Canny filter, you will have to input an image to it. So you can add those files over here in data files. Once you're added all these files, click on compile your project option. This basically doesn't compile, it just adds the files to your virtual machine that you will invoke once it is ready. It will take like half a minute to do it. So yeah, the console is ready. You can open it full screen in another tab and give the password. The password is on the left hand side on top of the console screen. You have to give this password to open the virtual machine. And here it is, the desktop of your virtual machine. Go in applications, click on terminal. So by default, all the project files that you create would be created in workspace folder. Right now, the files are not here yet, so you have to go back to your SuperVessel and click on sync project files. That will basically copy all the files to your virtual machine. Click it 2-3 times because sometimes it works on the first go, sometimes two or three times it takes. So yeah, it's ready. It has got the hello world example inside it. Now we have to invoke the GUI of SDAccel to create the project. So there would be an SDAccel icon on the desktop. Click on that. Click OK. Then, and while creating the project, we have to mention the type of device, type of FPGA that the kernel and the host application is targeting to use. So create a new project over here, file new Xilinx SDAccel project, give it any name, sync. So here we have to make sure that the board and the device are what we expect it to be. So we are currently using the Vertex 7 Alpha Data Xilinx card, which is there on the SuperVessel. We are using it on the Power Platform. So we have the PPC, that is a Power PC extension. LE is for Little Indian. And once you verify this, just click on Finish. So it will add the project files over here. Just make sure that all the files are included. So in Hello, there should be all the source code like the .cpp and the .cl file. There's also the tickle script file, which you can use if you want to use the command line version of SDAccel, or you can use the GUI to do the compilation. I'll show you the command line version. So in the command line version, just give the simple command line of SDAccel and the script that you're going to run. And it will start the compilation process, in which it will first go through the software emulation part, then the hardware emulation, and finally it will build a system that will eventually create the binary for the FPGA. This process will take some time, depends on the size of the application, where it takes about 30 to 45 minutes to do the emulation and compilation and create the final XCL bin file, that is the Xilinx OpenCL binary file. So for now, we can skip this step, and I can directly show you the run. So again, go to the project, and in that you have the project ready, hello world. So once your files are compiled, you have to go to the OpenPOWER VM tab. That basically will have the instance of your project that is created on your virtual machine, and select on what you would like to do. So if the application is compiled, then it will give all these options. It will give the options of which binary you want to select for the host and which binary for the FPGA. So as you can see, there are different binaries over here. Some binaries correspond to simulation and software, some correspond to the hardware emulation, and some correspond to the binaries that are created directly for the FPGA. So select the ones that have been created for the FPGA. Click on Submit, and it will automatically run your application. It will give the output in the data files window that I had shown you earlier, which had the input files option as well. And along with the output file, it will also show you the profiling summary, which will have all the details about the amount of time the API takes to execute, as well as the memory transfer taking place between the kernel and the global memory, and the global and the host memory. Yeah, it takes some amount of time to run this. Nah, let's try it again. It's taking longer than it should. I think the server is a little slow right now, so probably it is taking a longer time. Okay, so I can show you the output files directly because this is taking longer than expected. So in the output files, we have the screen log that will show the output that the kernel will generate. So this is what the output will look like. Um, in a hello world example, the kernel will just print out that it has received the following values from the host. And this is the profiling summary that I was talking about earlier. So in the OpenCL memory hierarchy, there are four or five different kinds of hierarchy. One is the host memory, then second is the global memory, which is common between the host and the FPGA. Then we have a constant global memory, which is also common between the host and the FPGA, but only the host can write to it. The FPGA can only read from it. And then there is the private and local memory. So this parameters will matrix will give the information about the bandwidth memory transfer between the kernel and global and host memory. And so this would be very important when you want to optimize your application using different pragmas and directives that are there in the SDAccel environment. So yeah, this was the demo of Hello World and SuperVessel SDAccel. Let me switch gears to Cappy. So Cappy stands for Coherent Accelerator Processor Interface. It's a protocol that was developed by IBM back in 2014 that uses the PCI bus to extend coherency between an accelerator and a power processor. So in a traditional I/O model where you're just using the PCI along with device driver, what happens is that the first step would be for the application to set up the registers and input data, which needs to be sent to the FPGA for it to start working on. Then it will go and invoke the device driver. The device driver will copy that input data from the virtual space of the application and into its own memory space. And then it will, and also it has got the memory map of the entire accelerator. So it will go and tell the FPGA that it has got some amount of work to be done. And the FPGA will come and grab the data from the device driver. It will then carry on the execution and complete it. And again, the device driver would be constantly polling the FPGA to see if the FPGA is done with its execution. And once it gets that interrupt or once it gets that result from the FPGA, then it will get the data from the FPGA and it will store it back to the application's virtual address space. So as you can see, there are three copies of data that are taking place. One copy is in the application's virtual space, second copy is in the device driver, and third copy is in the FPGA. And there are thousands of device driver instructions and operations taking place, which result into a great amount of overhead. Now, in many modern machines like IBM, Intel, they trim the device driver in such a way that there is no need to copy the data between the application and the device driver. They just spin it, or the device driver does a zero copy. But again, at that time, the application cannot look into the data that has been pinned or locked by the device driver. So that is another disadvantage of the IO attachment model. In Cappy, it's totally different. The first step will remain the same. The input application has to set up the registers and input data. Second step is where the differentiation happens between Cappy and a normal PCI. The application will go and invoke a layer called a power service layer, which is on the FPGA. It will tell the PSL that it has got some work for the FPGA, and the PSL will in turn do that work to the FPGA. So it totally eliminates the device driver operations and the overhead data associated with it. And the FPGA will come to the system memory. It will grab the data, it will access the data, read from it, write to it, and it will basically tell the PSL and the application's virtual address space that it is done with the data, and now the host can use it. So a lot of overhead that was associated with the device driver is eliminated in this case. So that is the high-level difference, very high-level difference between Cappy and PCI. I will talk about the details of Cappy in the later slides. These are the key components of Cappy. We have the coherent accelerator interface architecture, which describes the hardware uh, that is used to enable coherency between the host and the FPGA. Now, this hardware is on the FPGA as well as it is on the power processor, and it consumes a certain amount of real estate on the FPGA, but it is not that much that could limit the application's real estate. Then we have the accelerator function unit, which is the application that would be running on the FPGA, or I would say the application that needs to be accelerated in an processor accelerator environment. And then we have the PSL that I told you about earlier. It is the heart of Cappy. Then we have the coherent accelerator processor proxy hardware, which is present on the power processor. That is also one of the components that helps in maintaining the coherency between the cores that are running on the power processor and the PSL. So this is a very general overview of how the entire system works. The application function unit or the AFU would be there on the FPGA. It would be coded in RTL and with Cappy support being to be included in SDAccel in the future, the application can be coded in OpenCL, C or C++. And the application can be of any type. It can be a data intensive, computer intensive, like an FFT, it can, or like a Monte Carlo algorithm, or it can be a storage or an external I/O. And the host application will do the necessary data setup for the FPGA to start its execution on. So these are the key components of Cappy interface. So as you can see on the FPGA, there is a blue colored block called IBM supplied PSL, or the power service layer. There are three main tasks of the PSL. First is to provide caching. It has got a 256 KB 8-way set associated to cache on the FPGA. So for different applications, for example, if it is a image processing application where the accelerator has to work on pixels, it reads a pixel, does some work, writes the pixel and reads it back again. Then in that case, if it is able to store that data in the PSL cache, then it will save a lot of latency as compared to the case in which it has to go to the system memory many times over the PCI bus and do the same amount of functionality. The second job of PSL would be to provide the address translation. Now, since we are talking about coherency here, the FPGA and the host, they need to talk at the same translation level. So the PSL has got this memory management unit. It has got the effect tutorial at a stable, then a segment leukocyte buffer, and a translation leukocyte buffer. That basically makes sure that the application that is running on the FPGA, it is having the same view of data as that is there on the host. Then there's the PCI interface. The electricals remain the same as the normal I/O method. Then the cap unit. So cap unit, as you can see, it is on the hardware of the power processor, and so it is running at 3 gigahertz. And so whenever a core on the power processor wants to access some data that is there on the PSL or on the FPGA, then it will come and invoke the cap unit. The cap unit on behalf of PSL will make sure that the core will get that data. It will send a command to the PSL that it wants the data, and the PSL will respond with the latest copy of that data. And so that basically maintains the overview. That basically maintains the coherence between the hardware accelerator and the power processor. Then we have the OS. In a typical I/O model, what we have is a Linux kernel driver that helps the application talk to the FPGA board, and that has got a device driver as well. Now in Cappy, we have this Cappy accelerator library that is SDAccel that has got very simple APIs. So you can include those APIs in the application, and with those APIs, the application can talk with the FPGA board. Currently, that libcxl is part of the Ubuntu PowerPC package, Red Hat PowerPC package, and also IBM's proprietary AIX. Now, how this works is the application, whenever it wants to send some work to the FPGA, it will send a work item through the PSL, and that work item will contain all the information about the job that the FPGA needs to do. It can either do that, or it can send a pointer to the FPGA, and that pointer would be to a location in the system memory, and the FPGA can go to the system memory and fetch the address, which would have the job element descriptor, which have the information about the job that the FPGA needs to do. So if we compare it with the typical I/O model, as I told earlier, that the device server call will have to be made, and it will either copy or pin the data, and then it will do an MMIO to notify the accelerator. In case of Cappy, it's a pretty straightforward mechanism in which the shared virtual memory will notify the accelerator, and the FPGA will do its computations and update the results again back in the shared virtual memory. So as you can see, there are a lot of advantages of Cappy over a PCI. The first advantage, which the PSL is providing, is having caching mechanism, which is not there in a PCI interface or PCI traditional I/O model flow. Then it also has got so since we are not using any kind of device over operations, it results into a very easier natural programming model. Also, one other aspect of PSL is that it allows virtualization. So, for example, if you have a gzip compression engine on the FPGA, and if you want multiple applications from the host access that particular gzip compression engine, then it is possible. The PSL will work on the context switching, and it will allow different applications which are having their own address spaces work smoothly as possible with no stepping of one application over the other application's address space. These are the information about the number of instructions that a comparison between the number of instructions. So in a typical I/O model flow, you have got about 15,000 instructions to start the process of data preparation, and once the data has been sent to the accelerator and the accelerator has processed it, worked on it, and given it back to the FPGA, given it back to the host. In case of Cappy, it only takes about 500 instructions to do that. So the latency difference is huge. For the same application, we find that the application that runs with Cappy protocol over the PCI interface will be 40x faster than what it will take on a normal PCI flow. There are many real-world applications which highlight the performance advantage of Cappy over a normal PCI. And the first such real-world application that we had developed about a couple of years ago was the NoSQL IBM data engine, which utilized a power processor attached to an FPGA through Cappy, and it used flash drives attached to fabric channels to the FPGA. And so it was able to, and this system was able to create a new tier of memory by attaching about 57 terabytes of flash memory to the processor without the latency issue of a traditional I/O storage. In a typical NoSQL application, the requirement is that it should have a very fast application response time, and that's why it operates always in the DRAM. And since DRAM is expensive, cache is expensive, it's very difficult to scale that system. Cappy solution basically solves that issue by attaching the 57 terabytes of flash memory to the FPGA and back to the processor. And we found that for a 12 terabyte of NoSQL database, the deployment cost with Cappy solution was 1/3 of what it took for a traditional I/O deployment. And since the number of nodes also went down because of this solution not use too many DRAMs, we found that the operational costs reduced dramatically. This operation cost was associated with the networking, space, power, cooling, and operations overhead. You can find the white paper on this link. I will put it up on Slack. Now in SDAccel, we are working with Xilinx currently to include that support in XDAccel, and we're planning to launch it by the year end. So OpenCL has got this various generations, 1, 1.2, 2.0. The current and the most popular version that is being used right now is the OpenCL 2.0. It has got this feature called shared virtual memory. In a traditional OpenCL implementation, how for the host to interact with the FPGA, the OpenCL runtime will allocate a buffer on the host. It will allocate a buffer on the FPGA, and the OpenCL runtime will copy the data from the host buffer to the device buffer. So as you can see, there is a lot of memory transfers taking place and a lot of API calls for that. And when the FPGA is done executing its application, it will again copy the data back from the device buffer to the host buffer. In OpenCL 2.0 shared virtual memory, that copy of data is completely eliminated. The host and the device will have a single view of the buffer. They will use pointers to address the memory that is there in the buffer. So all the API calls and latencies associated with it would be eliminated, and also the unnecessary copying of data between over the PCI interface between the two buffers would also be eliminated. And since Cappy supports this in hardware, we believe that this would definitely be an advantage for Cappy OpenCL solutions over a normal PCI OpenCL solution. So that's it. Hopefully this would be out by the year end, and we will have good results with Cappy. If you guys have any questions, you can let me know. You can ask here, or you can ping us on Slack.
Awesome. Thank you so much, Ishan. I'm looking, and I don't see any questions coming in, so please, if you had any, let us know. There was one thing that some folks have been chatting on Twitter about FPGA support in OpenPOWER for various different functionality. There was a question, so maybe this is for you, Fernando, about enabling hashing acceleration on FPGAs. So I noticed there were some demos in SuperVessel related to the SHA-1 algorithm. So if you could tell us a little bit more about that, that'd be great.
Yeah, thank you, my friend. So FPGAs are great for hashing functions because hashing functions are bit manipulations and XORs for the most part. The SHA-1 hash function algorithm that's available on GitHub, and it's also available on the SuperVessel demonstrations, is a good example of how to do hashing in an FPGA and how to get good performance with almost no resources. So just to give you an idea, the hashing function based on the FPGA capabilities, using only at 6% of the FPGA fabric, will give you 12.8 gigabytes per second of throughput, which exceeds our available DDR bandwidth. So without lots of resources, you can get a very customized hashing function that will maximize your bandwidth and your throughput.
Okay, great. Thank you. All right, well, I don't see any more questions at this time, so thanks everyone for tuning in. And again, we're all on Slack if you have more questions there anytime. Thanks for tuning in. Talk to you soon.